right, everybody. I hope you had a wonderful lunch. So the challenge for the after lunch speaker is always try to keep everybody awake and prevent the food coma. And I will step up to that challenge and hopefully fulfill it. So in proper DNS fashion, people who work in the HTTP side of the world might use a who is slide. We in the DNS, we use a dig slide. For those who aren't familiar with the DNS, one thing I kind of cut out of this is like that long intro of RFC 1035 and how, back in the day, these great people created the first truly globally distributed, eventually consistent database known as the DNS, because everybody knows that. So before we get too far into things, it is my goal to avoid this. I've been this person and I feel bad when I do it. So if at any point you feel like you're trailing off into this space, please feel free to raise your hand or interrupt in some potentially creative way to spawn a new train of thought. Because the end goal for all of you is to walk away today with something that you didn't know when you came in, so that you feel like this was totally worth your time. Because that's my goal, is to make this worth your time. So do your best to make sure you get what you need out of this. So, real random overview setting here. We're going to talk a little bit about IoT in general, or how it's been addressed in the media as of late. We're going to then move into the previous paradigm of risks to networks in the form of denial of service attacks, and kind of how we used to think about defending the edge of our network. Then work into the signals that we saw on the internet that kind of hinted that this new thing was lurking around waiting to cause problems. Then the part that everybody wants to hear, the problems that were caused. And then after that, the things we've been doing since then to make our systems more resilient and to model out this type of behavior more accurately. So the Internet of Things is everywhere. There's devices in your home, there's devices in your pocket, and there's devices in the news. To pull a few recent ones out, the idea that now there's commercials which are speaking to the devices in your house to get them to do things is just the next fun way that somebody's going to break the Internet. You write a custom package for one of these appliances, you slip it into a cheap television slot, and all kinds of fun things happen. But this is the trend we're going on, where the attack surface is no longer just getting to the device, so traversing the ISP network to the edge of your house, through your edge router to something. There's now a number of other different ways to get to the device. But in this case, we're talking about a much dirtier, gross collection of devices. So these are things which in most cases were directly connected to the internet, so the challenge of finding them was lower, and the sophistication of the devices themselves was also lower. Now, we don't want to model this as if it's a new problem, because we've seen this before in the past. Mirai specifically was just a combination of a few known techniques combined in a very scalable way to create very clever mischief. So it exploited the fact that these devices had hard-coded passwords. They had a pretty, well, I don't want to say pretty efficient, because at the time, after people have ripped apart the code base, its efficiency is, been trivialized by engineers who would say that it is not efficient, but at the same time, it worked. So you get credit for that. And the malware itself. So to say that this has been done before, we all kind of knew that it happened before, and we'd seen what one could do if they compromised this many devices. And the last time we saw it was the Klarna botnet. Now, being an internet researcher, when this body of data came out, so if imagine instead of using all these home routers and DVRs to attack internet sites, you just ran massive numbers of trace routes, and you collected all kinds of interesting telemetry about the connectivity of devices on the internet. And then you said, well, we found a problem, we used these devices to make a unique data set, and then we deleted the malware from all these devices and published that data set to the internet. So that happened in 2012, and there was arguably more devices in that botnet than were in Mirai at its peak before NSNPy leaked the code base. But it didn't really hit the risk registers of most enterprises, because it was a one-off, stunt hackish event. I don't want to call it stunt hacks, that kind of takes away the cool scientific output of it. But we knew it could happen. Now, at the same time, we also knew that people would make moderately sized botnets with poorly written code. So this is an example of a Perl botnet that was running using our dynamic DNS service. When we took it down, there was 2,500 to 3,000 endpoints active at that time. And from at that point in time, seeing that many endpoints orchestrated in a botnet, it wasn't new, but it was seen as sizable. because at the time we were dealing with a different type of attacker infrastructure. So this thing could create that many new connections from that many networks, and it was, for this use case, sort of rare. Now, the reason we have to talk about the network a little bit is attacking the DNS is different than attacking a web server. And it's different because of the distributed nature of the system and the things that are dependent on it. So to start to talk about the risks and the exposures, we need to start to talk about the network itself, or the topography, or how we exist on the internet. So I know a lot of people here probably operate in clouds, right? How many people in here operate internet-facing infrastructure? Have routers on the internet, announce BGP, all those fun things. Now, if we did that 5 years ago, most people probably raise their hands because we didn't have the options that we did then. So these are the types of problems that will probably exist for fewer and fewer people over time, but they're kind of a huge pain. So if you imagine when you have this many points of presence and you're using a technology or an implementation of a technology called Anycast, the goal is to announce the same IP space from all of these places. So that way, when somebody tries to talk to the network, they'll go to the one that has the shortest network path. Now, we'll cover a little bit more about that when we talk about the previous defense models. But one thing that makes our network different than some others is that instead of using peering, where we walk around and have individual agreements with many ISPs, we work with a few very large ISPs that specialize in forming those agreements. Now, I guess from a risk perspective or just a decision-making perspective, the best way to think about this is you can go to a few people whose core competency is setting up these arrangements and having their network's connectivity be very diverse. Or you can insource that and run that sort of peering understanding and peering mapping infrastructure within your own organization. So do you want to outsource? Do you want to insource? That's kind of the big question there. So in our case, we're using a collection of tier 1 ISPs that have different connectivity around the world. So we're outsourcing that value and we're trusting that they're the ones who are putting together the closest maps for different regions. Now, why does this matter? So when I started working in this space, DDoS was very different. And that's kind of because the economics of the endpoint were different. So when we saw that Perl script running earlier, if you can compromise a machine, why are you going to install a Perl script that just throws packets? There's better ways for a criminal to make money off compromising that system. So it seems odd to do that. Now, this also assumes that all criminals are, rational economic actors, and homo economicus is like a real thing. But that's what we do in thought exercises. We like to make these kind of assumptions. But if you walk through the different list, you could be using that machine for click fraud, run it for a while. The second they notice, ransomware the box, try to get the money back, leave them with a bricked machine. There's all kinds of options. So deploying a Perl-based DDoS bot just doesn't make sense. So in a lot of cases, people would run these booter stressor infrastructures. And the whole goal here is to get a well-connected server and exploit the protocols of the internet itself. So are people familiar with amplification attacks? So I ask you a question, and you give me back a much larger response. And since you don't verify who I am, I can pretend to be someone else, ask a question as them, and then you'll respond to them continuously. One of the fun hacks of UDP, mainly deployed in Chargen, DNS amplification, NTP, the things that get the news in really big response bodies. So what criminals started to do is they'd go around and they'd find providers that allowed this spoofing. So because people on the internet agreed that you shouldn't allow traffic that didn't come from your network out into the world, in this fun little thing called BCP38, providers which didn't enforce BCP38 all of a sudden now had a value to criminals, because from those networks, they could issue these specific requests that would have a larger response that goes to someone else. Now, when I first saw the pricing models of onshore versus offshore, I assumed that offshore would be more expensive, because offshore it's cooler, from American perspective, it sounds like more exotic. The problem is it's going to actually direct the traffic to a different place. So having a server in the US is arguably more valuable. Not something I put together originally. The prices they're paying for bandwidth are relatively low. And one thing we started to see on different forums and other places was they were actually using some of the reports produced by CADA, a group that does internet studies and kind of tracks spoofability, So if you operate an autonomous system, you might want to go check it out and see like what they think of your space now. But the goal of this project originally was to identify problems with spoofing and use this to correct it. Whereas these criminals would go and they'd take a screenshot that their network allowed spoofing from CADA and post it to their website as a form of like marketing collateral. So now you have a well-connected machine connected to the internet. So what's your next problem? You have to be able to create these packets which will cause a large response to come at scale. Now, that requires some engineering. You also have to figure out all the different servers that you can ask these questions to that will respond, because most operators won't respond to these amplifying queries. Now, being a free market that it is, and the internet always enabling commerce, we started to see these things pop up. So groups would go out and they'd write engines to create these packets that would generate the large response, and they'd sell you a plan for access to the tooling. And the more you spent, the more cool attacks you got. So for people not super familiar, so in the cheapest package, you just get DNS, NTP, and SMTP. I don't want to say these are lame and played out, but most of the mitigating appliances have modules for understanding this in silicon. Now, some of these other more exotic ones, the fun stuff like the Valve and Steam engine amplification attacks, Quake server attacks, TeamSpeak. So they're just going out and finding any protocol that's exposed on the internet that will have a larger response, and they're selling you a way to craft those packets. So you now don't need to know anything about the internet. You just need to go purchase the server, pay this person $300, and now you have all the tools. The one missing bit is very specifically that list of amplifying things. So that goes back to writing a scanner. So you have to write something that's going to go out across the internet and monitor that these services are listening on sockets, and they're going to pass back that large response that you're looking for. Again, that takes engineering work, so it's something you can outsource and sell as part of one of these packages. It also means that criminal can now glue all this together for about, $400 or $500. Because their goal, wow, that is bleedy. Their goal is in the end to deploy this interface. So for people familiar with this part of the world, essentially, they want to plug in here a host value, so that's either going to be the host name of your server or an IP address. They plug in a port number, so like in the case you're trying to attack a DNS server, you plug in port 53, because that's what it listens on. If you're attacking a web server, 80 or 443, how long you're going to attack for, and then you pick from this list the type of attack you're going to launch. So this is the interface that the attacker has versus you as the defender, who pretty much you have NetFlow, you have some other things, but nothing as exacting as their interface to attacks. And people talk about the attack was constantly changing throughout the event. Yeah, I mean, if all you need to do as an attacker is click through a drop-down box, different things you want to throw at someone, yeah, it's going to change. So earlier we were talking a little about this amplification thing, and to kind of drive home how that fits with Anycast, I put together these childish drawings of what that might look like. So in this case, we have the well-provisioned box that the attacker controls existing in their ASN. Now, their autonomous systems. This is their connection to the internet or their neighborhood. Now, they've purchased this list of things that they can go ask these questions to, the scanning list, and the machines in that list exist in a number of other ASNs. So they then make a request to the server in this ASN saying that you asked it, and the response in theory comes to us. But what does that really look like? Okay, so the goal here is to look at the ASN path. So if we think about that amplifying server, in this case it's located in Ecatel's ASN, they're asking a server that exists in this NAP block. So for that packet to traverse the internet to get to our servers, it's going to go through whoever Enforce Entertainment has peering with, and then up through one of these providers. So as you start to think about how traffic is going to come to your edge, it's really based about how the networking of this amplifying server is connected to the internet and how you are also connected to the internet. So in this case, following our ASN paths, it's going to follow one of those three, depending on the shortest path principle, or in a more cartoonish form, it's going to hit different points on the edge. Now, when I say different points on the edge, what I mean is different data centers in different parts of the world. And that's one of the goals of Anycast, of announcing the same IP space in many places. you're going to have this traffic go to different parts of your network and in theory thin it out so it's hard to concentrate it in one area. So this was a classic model that we saw for a while where they basically would have they'd have the amp list, they'd have their list of open resolvers, but they messed up on the source port. So usually when you issue DNS requests, you use a randomized source port. This was something that they tried to fix early, or was a revision that was made post RFC 1035 where it used to be a static source port, but they ran into issues with spoofability. So when you have the misconfigured source port, very seldom can you concentrate a single source port when you're looking at a distribution of source ports received by a server. So all of a sudden on our network, we'd see this massive spike in net flow of UDP packets coming to us on source port 44444. That's not a real thing, and it's a quick way to identify a problem. So when you go back and you find the kit they were using to generate those packets that they purchased, that person didn't take the time to put a randomization function in that part of the packet generation process. And this is the fun that you get to play when people are purchasing this type of stuff, because then you'd see it pop up different times, and you knew that these people were using the same really poorly written code base. So this problem has existed for a while, and tier 1 network providers are kind of aware of that. So one thing that they introduced were these egress ACLs. So when we go to our providers and they're passing traffic back to us, we just say, you know, the only things that we have listening on sockets on these machines that we want traffic for are on port 53. So when that port 444 traffic is coming through your network, just throw it on the floor, because we don't have anything listening on that port. So don't deliver it to us. Now, for a while, these things didn't exist across providers. As the amplification issues grew and became, I guess, higher profile items, they made it into the product manifests for a number of providers and they became more common. The ability to change them is slow because you're making changes on very big core pieces of infrastructure. So normally you have to set it for at least a month. So it's not something that's going to be fast changing, possibly like a cloud provider profile. But the sense here was, we can now solve part of this problem. So previously we had all the inbound traffic on the internet coming to anywhere, and we'd have to write processes to look at those packets. Well, now we can insert in here this ingress ACL and we can say, well, the provider is only going to be passing us packets on these ports. So at that point we just have to validate, is this a DNS request? Is it a valid DNS request? And from that we tried to put together this notion of packet ownership, so that different people in the stack needed to understand what their application was doing to the packet and what it had to do to make sure that it was valid to pass it to the next person in the chain. Now, I know not everybody who writes software really enjoys nuancy network things, so this was kind of a fun way for us to engage with developers and try to explain to them how we saw this set of problems. Because the end goal is to create this body of known legitimate traffic, which, as we'll hear in a few minutes, gets harder and harder as things get written more efficiently. One thing to remember, if you start to look at this model, is that as you implement these ACLs, you will in theory see less traffic. This can be bad for metrics-driven organizations because now the number of attacks that you see is going to go down based on this change that you've made. So it's important to remind management of this defense and your great success in decreasing incidents by putting it in place, instead of a net decrease in incidents in general. Total framing problem. The problem now is the packet is literally yours. So each person now has to create this set of heuristics to understand who's looked at it before them and what they need to do to pass it on to the next daemon in the process, or to pass it on or throw it on the floor. And this is where the fun begins, of everybody working together to define what legitimate is. Legitimate in the DNS is a very dangerous bag. Part of that is because it's been around for a really long time. So a researcher at a German university, Christian Rousseau, did this really cool project where he went out and he scanned all the different resolvers that were listening on port 53 and would issue valid responses. And when he looked at it, he noticed that the versions of Bind they were running were well over 10 years out of date on average. Yeah, so when you're designing for the DNS, you have to remember that no one ever replaces their DNS servers anywhere. Or if they do, they're not where they need to be. So you have this problem of things don't work the way modern things should work. And a great example of that is the eDNS 0 problem. So DNS responses were originally designed to be pretty small. So we made a modification to that so that you could ask larger questions and get bigger responses, mainly to deal with DNSSEC. Well, it turns out somebody had made a series of appliances which were very popular in India that had the DNS stack implemented in an interesting way, where when you sent them when you set the flag to have them ask you again over TCP, their response would be, okay, SYN, SYN-ACK, SYN. And basically, you would get in a battle with the device where it would just keep sinning you and acking sins, but there would no further interactions would happen. And guess what? One of those devices is going to crash. But it's not yours, it's theirs. And then you get a call from them as an ISP saying, why are you denial of servicing my device? And you have to spend all this time going out, collecting data in PCAP so you can show them that they're not able to process the response correctly. So when you start thinking about the different auto mitigations, we also have to consider that there's so many different things in the wild that use the DNS that might not be able to tolerate these changes, that we need to be able to collect the level of telemetry to kind of deal with them in a graceful way. Because the worst thing you can do in that case is just, they put an abuse ticket in saying you're denial of servicing them and just closing the ticket, because now they'll never know. But if you take the time to look and you have a PCAP and you explain to them, there's a fundamental flaw in this appliance. Can you tell me what kind of appliance it is? Then you start to get a better understanding of the things that exist in the environment. Another fun case in the DNS is the delegation chain. So if you can imagine, somebody decides that they're going to use you as a DNS provider. They go to COM and they say, you know what? For my NS records, Dyn is now responsible. But it's a weekend, and they did that late on Friday, but they never took the time to create the zone in Dyn's context. So as far as .com knows, Dyn is going to serve responses for example.com. But example.com was never created on our name servers. And it turns out example.com is what's used to serve updates for a large number of CPE devices. So over the weekend, when they all look for download.example.com and they try to do the resolution chain, there's no zone. And you can't cache that refused response. So you have hundreds of thousands of requests just flowing through the internet because somebody delegated a zone to you and the refused response isn't cacheable, so you just ask again. And you get paged to figure out what's happening. And then you figure out, oh, anybody can delegate what they want, wherever they want, pretty much, and it's up to you to kind of engineer around that problem. And then last but not least are these two fun bottom groups. Authoritative exhaustion DNS attacks and distributed non-spoof TCP attacks, which we'll go into now. So from a body of data, the authoritative exhaustion attacks are very interesting because they're so noisy. So in August, we started to see these large volumes of queries coming in that didn't meet those booter patterns that we'd mentioned before. So they weren't cpsc.gov, they didn't have gross charge-in strings. They were there, they were properly formed, transaction IDs were rotating, but they had some common characteristics. They had this 12-character subdomain that was missing a few key letters, so it hinted that it is random, but the thing building the random string doesn't have a full library to it. And they were targeted pretty well across our edge. In the case of getting across the edge, that means they actually had infected devices in most of the world because they're going to an Anycast location. So to get to that Anycast location, they either have to target it directly or have presence within proximity of that part of the network. And that is not very common. One thing, so at that point, because it's UDP, you almost automatically assume that some part of it is spoofed. But because of the age of the DNS, there's another wart you can use to solve this. It's the OX 20-bit case randomization. So this is another security measure where you'd use the case of the string to help reduce the issues with spoofability. So in this case, when we looked at, and very few resolvers have implemented it, especially very few that you see a large number of queries coming from. So all of a sudden, when we see that random subdomain and we see case randomization in the strings, and we see that those are coming from resolvers that have implemented it because we track who has, we know that something is asking a resolver that we know this question. And we know that it's asking it a lot of times very specifically because it knows that this random string will not be in the cache. Interesting stuff. Other key points, so the TTLs on the packet were also very well distributed. So you know they weren't coming from a single source to many places. Let's get for now. So the only theory that came up on why anybody would do this was that they were testing out a clever hack to response rate limiting. So response rate limiting was this other thing that they try to do in the DNS to reduce issues with amplification attacks. So if I get asked enough times for a domain, I'll only answer it 1 out of 5, 1 out of 10, 1 out of 20 times to kind of reduce the problems you'd cause on other networks from amplification. And a lot of people have started writing their own resolver stacks, which we'll talk about a lot later. And it turns out when you start to roll your own set of logic for something that's this complex with this many nuanced cases, you could have an issue fall in there. So that was the theory as to why this attack started to be included more often. But the only way to know is to look deeper into the recursive layer. What is the recursive layer? So again, it's very hard to assume what people know about the DNS because when you are obsessed with it for years, it seems like it's just one of those things that everybody should know about when it's not. As a matter of fact, my grandparents and my parents pretty much had no idea what I did until the attack happened. And they were like, oh, that. Okay, I get it. That was on the news. It's the truth. So to put this into perspective, you have a stub resolver on the end here. So this could be your desktop computer, which it probably isn't. More likely it's your cell phone. That's just the best icon that I had at the time, and it fit the boxy fit. It has no idea where Twitter is. So it asks the resolver. Now the resolver that is most popular in the world and spray painted on walls during revolutions in certain places in the world, 8.8.8.8.8. There's many others. It'll be auto-configured by your ISP in the event that you don't alter it. But that is the thing which you are asking questions. And it is that resolver's responsibility to dutifully go through this chain and get you the correct response. So that resolver then goes, oh, twitter.com? Oh, it's the root. Now chances are that's cached because the TTL is very long, but in the event that the cache is completely empty, it's actually going to create, I think it's 10 or 11 queries to the different root hints or root servers to say, hey, who's responsible for COM right now? And it gets back an A record for who's responsible for COM, or in this case, many A records because the cache is empty and it'll get one for each of them. And then it'll go and say, hey COM, who's responsible for twitter.com? And of course, there's many presences of .com because that's an important resolver. And you'll get back all those responses. And then finally they'll say, oh, Dine's name servers will tell you where Twitter is. So then that recursive resolver then comes and asks Dine's authoritative resolver, where is Twitter? And we hand back an A record, A and quad A. The IP address you can talk to find the server for Twitter. Now this is all going on in the background. These are things that never matter until they stop working and things get really awful. But remember the number of queries in that case, just to get this simple response of where does my web browser go to get the content for twitter.com. So in this case, we're looking at one of these authoritative exhaustion attacks, and we have a recursive resolver. So we see all these individual IPs asking us questions about this domain with the 12-character subdomain added. So during that period, we take the number of queries asked and we look at how many queries per second were we seeing from these different sources. Now, part of the goal here is to figure out what is going on. Because it's strange. It's not enough to cause a problem, but it's enough that it is generating a lot of data. And whenever anything generates that much data, you have to just dive in there and start figuring it out. So when you see these distributions, they don't make a lot of sense. Some are very small, some are very high, some have some larger variability to them, and you start to wonder what's going on. So of course, at this point, you reach out to an embedded device person, and you're like, hey, what's going on here? I'm seeing all these queries coming from this individual source IP. As a network person, I see this 2,000 plus queries per second, and I'm like, carrier grade NAT. That is the carrier grade NAT for an ISP somewhere, and there are many devices behind that IP, but we only see that one IP because that's what's fronting to the internet. Must be that. I go to the device guy goes, no man, you're totally wrong. What you're seeing is a better provisioned device, so more RAM, more CPU, on a better connection. So that's one machine with a better connection generating way more packets. All right, maybe. So what do we do in that case? We reach into the dirty bag of internet tricks and we GeoIP those addresses. This will not turn into a 45-minute rant about how GeoIP is dangerous, but it is. We'll do that later for a few seconds. But I had to concede because in this case, that bottom left right there, that's Iran, and that's from South Korea. Iran, not the best connectivity, probably a not performant client. South Korea, very good connectivity, possibly a better client. Now, you never really know because we didn't have a chance to fingerprint the device during this time. It was done after the fact. But it started to increase the plausibility that individual devices could ask a lot of questions. Then, of course, you go out and you try to connect to these things to see what they are. But you're a little late because the data is old, so it doesn't really work the way you would have hoped. And then you do the gross GeoIP thing and you start clustering them all. And this is a great time to point out why GeoIP can be a problem. So when you look at these numbers and the percent of traffic, you see the US is at the top. And earlier, or in all the news reports you've read about this incident, most of the devices that are impacted are not in the US. So at this point in time, we're just sitting there very confused about what's happening with the world. Then the best thing happens and the attacker leaks the source code onto hack forums, and you can go out and you can figure out exactly why this was happening. For a researcher, this is like Christmas. Specifically for this specific statement. So in the event that that device can't find a resolve.conf entry, it's going to default to one of these 4 addresses. These 4 addresses are all companies in the US. If you use GeoIP based on these addresses and not the unicast addresses they'd be querying you from, that's how you get the 30%. So the world made sense then, because a lot of people use these defaults or configure them anyway, so you have some confidence that you're not crazy and that you're starting to understand what's going on here. Because the assumption is always that you're crazy. Now the odd thing about this was the duration of these attacks. Now this is where you get together with your friends and you play Sherlock Holmes and you're like, why were they only 5 to 7 minutes long? And you try to draw some conclusion to lead an audience to think that you can figure out more things than you plausibly can from just that type of signature and data. You can't. Nobody knows. Then October 21st happens and you get a lot more data about this stuff. Now, before I go on, it's always important to take a pause for a moment and say, before this incident happened, a few months before that, I handed over my keys to the core routers. So when this was happening, I operationally was useless aside from collecting data and analyzing network traffic, which to me is a wonderful place to be. But for our poor operations and customer support people, they had a really bad day and they worked really hard, and I love them for it. But I'm going to talk in a very excited manner about this data, and I don't want to take away from their awful experience because I find it so exciting. Because it is really awesome. Okay, so it's the morning of October 21st. We're actually all hanging out, working, and in the morning there's these blips where we see the 12-character random subdomain traffic hitting 2 of our customers in a semi-close succession. That's kind of interesting. Well, we see this all the time, so you don't really think much about it. You save the data sample away. Its priority doesn't warrant interrupting the things you're working on, so you set it aside. Then more attack traffic comes in, hitting different pieces of our infrastructure. Different types of attacks hitting different things. So if you can imagine on a NOC dashboard what this might look like, depending on how your network operations center is set up, or depending on how your monitoring is set up, it's weird. Bandwidth levels are elevated in different places, and at this point, it's just somewhat confusing. Now, earlier we were talking a little about Anycast, and how in the wonderful world of Anycast, things usually go to the closest place. Now, that becomes a bit of a problem when we start to think about stateful interactions. So a good way that I've been trying to explain how to think about this is, when we start to see this traffic pop up, depending on how the ISP is peered, when they're attacking different parts of our infrastructure or different portions of our IP space, they might end up in different data centers based on which provider is announcing that space for us. And the best way I think to think about that is, if you imagine an ISP in Hong Kong and it's attacking 3 different IP addresses, and those are each announced over a different provider, those might end up in slightly different places. Now we do that partially to help distribute load across our edge. So it becomes a problem when you're trying to understand the mechanics of where or how a thing is working, because in a sense, they might not know that their traffic is hitting these locations. What does that look like from a picture standpoint? So in some cases, the peering arrangement's very simple. So there's only one path they'd take that might get to our providers. In the case of others, there's 4 different ways. So we share 4 different paths, and that might cause more variation in the endpoints that traffic lands on. So you can imagine for the NOC, that gets scarier and scarier when all of a sudden it looks like the attacker has figured out a way to kind of like play the fiddle of your edge, when realistically it's some nuances of peering, essentially, and their choice in endpoints. So while the attack is going on, I start freaking out because we've been playing with this tool. If everybody hasn't checked it out, go grab it on GitHub. It's a very clever tool that goes out and it looks at the SSL certificate and some other components of an IP address, and then it draws a conclusion about the manufacturer. Because in most cases, the manufacturer has the same cert on all of their devices. So from this, you can say, at this point in time, this device was this thing. Because that, from a data analysis perspective, my goal here is to say, I know that traffic wasn't spoofed because at this time, that IP represented this device, and this device is susceptible to this very specific malware. Now, as I'm doing this, I'm freaking out, and I'm using a lot of resources to do this mapping because the timing, the time between you seeing the packet come from them and you doing the fingerprinting starts to get more and more important depending on different networks in the world. And part of that's based on how their DHCP lease rotation works. Some networks will rotate daily very specifically so they can charge you more money for a fixed IP address. Now here in the States, that's not really a problem. If you're a Comcast customer, I've had the same IP for like 2.5, 3 months maybe for $0 extra. And in other places, you know, like a power loss or something like that can cause the device to get an IP reset. So part of the reason for pointing out the timeliness element is if this event starts to happen and you're interested in doing this, understanding the time between seeing attack and time to fingerprint becomes more important because it increases your confidence that you know what the thing was. And the DHCP thing was just kind of like another cool little variable you can throw in there. Now, as this known Mirai signature is coming in, and we're rushing around to fingerprint things, this other body of traffic comes through. And this other body of traffic, you can't say it's kind of awesome, because that's not respectful, but it's very creative. So in the world of the DNS, this subdomain problem gets interesting. So the subdomains we were seeing before were 12 pseudo-random characters. Now all of a sudden we're seeing subdomains that were created from Microsoft support phone numbers, O'Reilly book names, GitHub project names, things from Tumblr. So the notion of random that they're now using defeats most n-gram analysis. So if you're familiar with n-gram analysis, there's common combinations of letters in English words, and sometimes that's something people use to classify traffic as being generated by a machine or not. So now what they're doing is they're taking knowns, they're taking existing strings on the internet and they're using those to defeat that "are you a machine" style filtering. So you're trying to classify this stuff, it gets weird. And in some cases, you know, it's just strange, like a Microsoft support number, that's odd. Now, the volume of unique strings that we saw coming from different places was well over 10 megabytes uncompressed if you just separate the strings off the subdomains. So not being a true scientist, I'd say that's not on a device in your house. It's just way too big. You're not going to push around 10 megabyte blocks to devices. It's just too much data. So chances are this is another set of machines generating this traffic. But if you can, so let me get my timestamps right. So this 11:08 was the time we saw the start of the SYN traffic, and this started at 11:20. So about 12 minutes apart. Yeah. So the poor knock is sifting through the. So I'm obsessed with trying to figure out what machines are where, when, at what time. Then this starts rolling in, and the question is, it can't be what we thought it was because that thing can't do this. And from a mitigation standpoint, it's just like it's a different problem. So this is what life is like. It's hard because you want to be excited because you're seeing all these new and fascinating things, but at the same time, life is bad. So now we're going to talk very specifically about why things are bad. And it's all about caching. Now, Depending on your discipline, you have to deal with caching somewhere, whether you're a front-end developer and you're dealing with CDN, whether you're a database developer and you're dealing with Memcache. The recursive layer is our global caching mechanism. And the TTLs on the records in those caches are pretty much lifeblood. It's like the anchor of power. It's like once that TTL is gone, or once that TTL is halfway gone and their prefetch happens for those resolvers, if your property is popular enough, they're going to come and ask for it again. Now, one of the things that came up after this event was this battle about TTLs and whether you should have longer TTLs, because if you had a really long TTL, this wouldn't have impacted you. Because you'd have a really long TTL, the record would have sat in the cache, and you would have gotten a response. This is not a good debate. People usually set TTLs for very set reasons. So if you're using a number of CDNs, you're going to have short TTLs to switch between CDNs. If you're using cloud infrastructure, chances are you're going to have shorter TTLs in the event that you need to switch hosts or something of that nature because they're ephemeral. And simply put, if you have really long TTLs, the attacker just attacks the host. If you have really short TTLs, the attacker attacks the DNS. There's no right or wrong. It's a use case thing. There's a lot of blogs and things that came out that confused a bunch of our customers. So there's like a lot of heated debates about what the right thing to do here is, and it's always subject to what you're controlling with the DNS itself. Now, when we talk about the cache and some of the issues with caching, the other problem that we started to experience was with the thing that I love so dear, which is IPv6. So for those who aren't familiar, in IETF land, the use of IPv6 or having a resolver by default ask for a quad A record is called happy eyeballs. I didn't realize that's a strange thing to call it when you really think about it. But yeah, so happy eyeballs. So now the best example is when iOS decided to make the change. The way they implemented it was every time you need to do a DNS lookup, the iOS stub resolver is going to issue an A and a quad A query. When it gets the A back, it'll still wait like 0.25 milliseconds for the quad A because it really wants to use the quad A response. Now, from a resolver's perspective, now every request is at least 2 requests. And when the caching layer goes away, that means that there's twice the load. So when prefetch happens, now instead of asking for one thing, it's asking for 2 things. And when we were talking about people writing their own resolvers, chances are, if you run a large set of recursive resolver clusters, you have some custom needs, you need distributed cache flush, you have to start writing all your own things there. One of the things you don't think about is back-off timers. So when you're not getting the responses that you think you should be getting, some people decide to ask more often. That's not good. It's very not good if you're the one being asked. Now, on the opposite side of that, there's another resolver company that uses this thing called answer with last known good response. So even though the TTL's expired, they'll still respond with the last thing they knew to be accurate for that request. That's a novel idea. So that's now back up in the IETF as to if that should be a suggested implementation in the DNS. Now that introduces some other very odd potential risk factors about initiating a DDoS, basically to keep a record stuck somewhere. Because nothing's ever clear in technology, there'll always be a fight. And who wins, no one knows. So what we call wave 1 at this point has started to die down. And in retrospect, calling them waves is not the best idea because it's more just the signals the attacker sent, the C2s, the durations they sent ran out. And then they came back, and they came back attacking everything instead of those individual pieces of infrastructure that we saw before. Now we saw all those flows hitting all the different infrastructure endpoints at the same time. And we also saw some other traffic, which it later was shown to be another fork of the Mirai botnet, and a return of those strange and protocol attacks. So now you get to the fun parts. Oops. Now you get to the fun parts of basically figuring out a series of mitigations to deal with this new volume of inbound traffic and rate limiting accordingly. Now, one of the problems you have with rate limiting is if you start rate limiting known popular resolvers that are trying to refill their caches, they get more aggressive. So it turns out rate limiting in that case is a very bad idea. But you don't learn that until after you do it. And the best part is when you reach out to the operators of those resolvers and you say, excuse me, did you know that the default behavior of your resolver is to do this? They're like, oh, wow, that's not good. Yes, it's not good. But we're all learning together. And that's what's important, and that's why we're here. Right? Because if we never talk about these things, how are we going to fix them in the future? So if you have anything that deals with the DNS, make sure you understand how its back-off logic works in the event that it doesn't get a response. And that's anywhere in the stack, because recursive resolvers have similar issues. Now, one thing I thought was really important to put on the end of this, well, not in the end, but as a part of this, is what do we do? So after the event happened to us, more and more news items came about other networks that were seeing these types of scans or attacks. The biggest one being the Dutch Telecom 900,000 endpoints impacted news headline. So that came in, and I got a call from my boss, and he's like, Chris, what's this? 900,000? That's a lot of stuff. Not only is that a lot of stuff, but it's all in Europe. And anybody who has to deal with the internet in Europe knows it's a very dense place. So if you were to have 900,000 infected machines in Dutch Telecom, you would have a very big problem for delivering services in Europe. But what do? Do you just sit there and cry? No, you have to think about different ways to contextualize this news and at least make your boss think you know what you do. Let's be honest. You need a way to say, I can rationally pick apart this problem. Granted, the solution might not be the best, but here's a rational approach to deal with it. So what do? We go out there and we say, okay, DTAG's got 900,000 infected devices. DTAG's autonomous system number is 3320. Okay, so we know its sphere of influence. Now we can go out and we can figure out how many net blocks are in that sphere. Now there's 516. Chances are not all of these net blocks belong to residential customers that would have impacted devices. So we can go then and we can start looking at the registry information for who owns some of these blocks. Not only that, but they're located around the world. Now there's a few red herrings in there, like the block in Hong Kong, they're announcing for IBM. The block in Switzerland, they're announcing for a finance provider. So we go through and we kind of whittle these down, and we get to a number of net blocks that we're comfortable with and most likely have consumer endpoints in them. So this would be a potentially impacted population. So we're there. Coloration. So who's here is familiar with RIPE Atlas? No one? Awesome. Okay. So, no, it's a good thing, because now this is the thing that we're going to learn. So if you can imagine, there's a whole bunch of internet nerds around the world, and it turns out a bunch of them in the Regional Internet Peering Exchange, so the European Internet Operators Group, decided, you know what we're going to do? We're going to develop this platform where we'll distribute these small devices that you can plug into your home router, and you can use them to take internet-wide measurements. Now this is very popular in Europe, so there's a lot of these sensors in different networks. And if you go to RIPE, you can sign up for this and you can get one of these. Comcast is a big sponsor. And from that, you can create maps of the internet. So I can run a DNS request from a probe in someone's house to figure out how it's going to resolve. I can run a trace route from their house. I can run a trace route from their house. If I can run a trace route from their house, I can figure out how their individual consumer connection is going to get to my edge. Not only can I do that, but I can look at the points along the way that this traffic is going to go through. So in this case, I started to look, where is the DNS going to resolve? So if you go and you look, and you have all these things make DNS requests, and you see where they hit your edge, we see, okay, most of them go to Frankfurt, and the contingency, they'll go to Amsterdam and Warsaw. So this is a routing announcement that we have to drag some traffic off the region in the event of an attack. Now from there, we did the DNS responses. We know which edge site they're going to hit. So now we're going to run a whole bunch of trace routes, and we're going to figure out what different pieces of infrastructure do these machines traverse to get to us in the first place. And we find some common links. We know where their peering points are, and we see that NTT has less peering points than Telia, which makes sense because Telia has a better European presence. And we see the level 3 handoff. So from here, we're starting to understand what their network looks like. And if there's 900,000 infected things in their network that start to try to get to ours, these are pretty much the 4 things they're going to have to go through to get there. Okay, so now we understand where their peering points are and where the traffic is going to go. We can start to understand more about failure within their network. So in the event that that peering point with NTT fails, where's the traffic going to go in that case? And really the whole goal here is to just get a better understanding of, is there a way that we can change our announcements to redirect this traffic outside of Germany or outside of Frankfurt? And the answer is yes. So we can change our announcements to drag more of that traffic to the Warsaw and to the Amsterdam POP by getting it to prioritize the level 3 peering point. Now that could cause other problems for level 3 traffic egressing DTAG's network, but we'll solve that when we get there. Now, that's how we started to contextualize the news. But one thing that people probably want to hear about is what has happened since then? What does this continue to look like? Now, there was a group on the internet that started posting some wonderful things on Twitter. And of course, they launched a whole bunch of attacks around Christmas. I don't know if anybody in here is a gamer, but for gamers, you know, Christmas has turned out to be not that fun time of year. Thanks. But then after that, we were hit by a few more attacks, and over time, they got smaller and smaller. And the reason for that is when the source code leaked and more people could use it, the population of devices being fought after was fixed. So now you have more people fighting for the same infected population, so you have less power in more places, right? It's like an infection model. Now, like most things, you'll have these ingenious folks, and the ingenious folks will try to figure out new places to put this malware. In one case, it was using an NTP update mechanism in some equipment to try to spread it via the TRO64 and TRO69 vulnerabilities in the provisioning equipment. So they were trying to seek a new population. And if they were to get that new population, now you'd have a net new body of devices that could be infected. Now, that didn't seem to work out too well, because the DTAG thing didn't actually cause 900 infected endpoints, it just caused a lot of news. But that didn't stop anybody, because then we started to see these Java RMI on TCP port 1099 infections with the same set of binaries. And then the news came out about some new default passwords. So people are increasing the search space, right? So they're seeking out new default passwords so they can get new devices that way. They're also seeking out new issues with daemons on ports in the case of the TRO64 and TRO69 vulnerabilities, all seeking to expand these populations to get net new devices to infect. So that's the Mirai side of things. Now, one other thing that's kind of important to note is that the DDoS thing is a problem, but there are other problems associated with this trend. So we've started to see more use of residentially impacted devices for proxies. So if you operate in a form of e-commerce and you look at who's signing up for subscriptions, and you do some pairing of like a credit card and a location, because most people have some geo blocks like that set up that if somebody has a credit card from the UK, but they came in from an IP in Florida, you're going to increase their risk score. Now, over time, recently, we've started to see more of these infected devices being used as proxies. So this is giving somebody access to IP space that they normally wouldn't have, so they can make actions on credit cards they have access to in that locality. It's a better use of a compromised endpoint than just chucking packets, especially from a business perspective and from profitability on their end. Now, the other side of this, with the recent large number of data dumps, if you think about all the large compromises in different places where they just throw out onto the internet a lot of usernames and passwords, this is also a phenomenal edge for account stuffing. And the first place people usually see this is in gaming companies, because that's a popular audience for this. But now, if you think about the rules you have in place on your edge, when people make requests with a password, how are you understanding those rates? Are you checking the number of username, password, authentication attempts in total? Are you tracking that by individual IP address? Are you tracking that by individual machine on your edge that's seeing that request? As they get more diverse and have more presence, we have to start thinking a lot more about how we are modeling out their behavior to understand if these things are starting to pop up more often and how they're using this network. And that's why it's the notion of like, it's only the beginning. Chucking packets at stuff is probably like the lowest level of use of one of these devices from both a monetization and a true utilization standpoint. And the thought is over time, we'll see more of these advanced cases where instead of being just a means of creating packets, they're kind of like a platform for delivering other awful malicious services. In conclusion, information about how to deploy these things is ubiquitous. You can go out and just kind of like search around on Instagram and you'll see kids, setting up nets for like $5, $10, $15, advertising openly on social media. Great idea. And the population, oh, yes. Oh, no, go ahead.
Is there any way for a single provider, DNS, to be able to deal with this kind of disaster? Does it require enterprises to have multiple DNS providers?
So our suggestion is yes, definitely have multiple DNS providers. Mainly just from a risk perspective, it's never good to assume, monoculture is never good. And it's just a good idea to have two providers. Now, there's some issues with implementations of DNS tricks. So if you do CNAME at the root type things, that's not an RFC standard feature deployed across resolvers. Now, the IETF right now is working on resolving that by drafting some new record types. So hopefully in the future it will be. So yes, definitely have two providers. Definitely. It's too risky not to.
And one question: what do you think is the purpose of this? If you take out the government, the foreign governments trying to harm business, if you will. What's the purpose of this? The fact that I can do it, or they're trying to make money off of these attacks?
So I think if you think back to, I think it was last summer, the DDoS ransom was very popular. Now, it's hard, so from a statistical standpoint, I'm not making any claims about access to data, because saying that you have access to the number of ransom emails that were sent out, the number of companies that received them, and the number of companies that paid them, you can't know because a lot of people won't talk about it. So that's the first problem. Like, we as a business community don't do a good job of telling other people about these things. Because if we had more transparent reporting, we could say, 9 out of 10 people didn't pay the ransom. That'd be a comfortable thing. But we don't know. We do know that some people have paid ransoms, so that will encourage these groups to go back and continue to do this. And as the media presents that problem, and they present, DDoS-based ransom is on the rise, more people are going to do it because they see it as a viable business opportunity. So I think a lot of it has to do with finding out ways to monetize their current infrastructure. And then in other cases, it's a way to express power. So some criminologists, I think there was a paper coming out from one of the major European universities where they actually went out and they interviewed some of the people who were operating these DDoS, specifically the boot or stressor infrastructures, and talking to them and doing psych profiles to get a better understanding of what caused them to do it. In a lot of cases, it was an expression of power. So if you're in a place and you don't feel powerful, and this is a way that you can go and show the things you can do, it's an outlet. Again, I'm not a psychologist or anything like that, but other people are doing research into this. So it's a great follow-up area. Does that answer your question, or? Okay, great.
Let me just get you on the mic for the recording.
Oh, sorry about that. So close.
I was hoping to kind of bring it back to the beginning, and you were talking about Internet of Things, and I was curious what you thought about, or your sort of anxiety level, so to speak, over things we might hear about on, say, TV or something like that, regarding like Internet of Things. Your kid's internet-connected spaceship he got for Christmas. Internet-connected Tickle Me Elmo, or what have you. These things that are just on the network. You don't have much control. You can't configure it to have multiple DNS. There's just a million of these things shipped, and kids turn them on, or what have you. You turn it on for Christmas, and now all of a sudden they're doing crazy things to the network or the internet. And is that? I feel like that's the kind of thing that's sort of talked about as a dangerous thing, kind of like in a very generic sense. And I wonder if that's. Does that resonate with you, or is that more of like a scare kind of tactic stuff?
Awesome question. So my sample set for this is a bit skewed, mainly because I feel awkward going into stores and purchasing children's toys, because right now we just have dogs. But so like in my test network at home, I have isolated out an Alexa, a Google Home, the Hue, the Samsung Smarter Things. It's most like these home automation platforms. And then I'll also go out and get collections like the smart light bulbs and all that stuff. Now, you can tell who has thought about this and who hasn't by just doing some initial port scans of the devices. It'll be very telling when you look and port 23 is still open with admin as the default creds, and that's on a device that was purchased recently. And the scarier thing about some of those is they're not cheap devices. Now, in other cases, I think it's the Philips Hue does a very good job outlining all the open source software that's running on it, and you can even go and see like what versions if you go to its homepage, because at first you're like, oh, I got you. You have something listening on port 80 on this WRT device that I just plugged in my house? And you go look, and what it is it's a static web page with all the versions of the software that are running on the device. Other devices have encouraging firmware update rates. So there's a lot of signals of people learning in there, but there's also the signals of just huge flaws in system-on-a-chip architecture. So I think the cases where I've seen more hopeful signs are people who have more of an ecosystem around the device. So it's a device with a web UI and some updatable components versus some of the things where it's like a buy, plug in, hope continues to work. And sadly, the price point on some of those, you don't buy your way out of insecurity. So is it a problem? Yes. Is that problem distributed evenly? No. And a lot of it comes back to like some of the systems on a chip manufacturers. So I think over time, as we study this more, we'll find common issues with specific manufacturers in the lower tiers. But there's also some encouraging points of like platforms specifically developed for delivering these services that provide that manufacturer better insight and better updatability because they're using a common core set of libraries that they can just basically then go and have built-in mechanisms to push those updates. So yeah, I wouldn't be over concerned. Like the dishwasher has a directory traversal vulnerability news item. When I saw that, I was like, that's weird. Is it writable? Like, can you put anything in there? And I think the answer to that was no, but it made for a great headline. Does that answer your question? Or I can follow up with you after too, because I love this stuff. Anybody else? I think I'm running low on time. I hear people in the hallway. All right. Well, thank you all very much for your time.